Today we link two big ideas: how to measure linear association with the correlation coefficient, and why correlation doesn't automatically mean cause and effect. It's like seeing umbrellas and puddles together. Yes, they appear together, but one did not cause the other. Think of R as the straightness score of the points. The more the points line up like a ruler, the closer R is to 1 in absolute value. If they look like a fluffy cloud, R is closer to 0, and there is no linear association. Scatter plots tell the story before the math kicks in. They show us if the relationship is positive, negative, nonlinear, or non-existent. Without them, you might trust R to describe data that actually curves like a banana. And bananas don't yield a particularly large R. We just turned 10 data pairs into one number that says pretty straight upward line. R is around 0.92, which means strong positive linear association. Not perfect, but your ruler would be pleased. The cloud of points leans up and right. That's the positive linear pattern. The wiggle is the real world reminding us it exists. Rule of thumb: if you can balance a ruler on the plot, R is large in absolute value. If you need a pillow instead of a ruler to cover the cloud, it's close to 0. Outliers are like plot twists. One surprise and the whole story changes. Deal with the drama queen point before calculating R. A strong correlation does not prove that one variable causes the other. Both may be driven by a hidden third factor, what we call a confounder. For example, sunscreen sales and pool attendance both rise in summer, but it's the season driving both, not one causing the other. Causation is not easy to prove. A strong correlation alone is not enough. We need well-designed studies to rule out confounding and bias. Experiments with control groups and random assignment give the strongest evidence, while observational studies are more limited. That's why in statistics we always ask not just whether two things move together, but whether one truly influences the other. Observational studies watch the movie. Experiments direct the movie. One gets popcorn, the other yells, "Action!" Design of experiments is an important statistical tool because it allows us to actually test for cause and effect. By using randomization, control groups, and replication, we can separate real effects from coincidence or confounding. In short, experiments give us the closest thing to a statistical truth serum. Pick C. Remember, if you want cause and effect, bring a good study design, not just a pretty scatter plot.